Great.
Right. Hi, everyone.
Oh, go ahead, Peter.
No worries. Hi, everyone. Welcome to the Causal Inference Seminar. Today, we're very excited to have Dr. Trang to present at our Causal group. She is an assistant scientist at the Department of Mental Health here at Hopkins, and she's also a member of the SOURCE lab. Today, she will present on sensitivity analysis for principal ignorability violations in estimating complier and non-complier average causal effects. And without further ado, I'll hand it over to Trang.
Thank you. Betsy, did you want to say something?
I just wanted to say thanks, Trang, for agreeing to present, and thanks, Peter, for organizing.
Thank you, Betsy. Thank you, Peter, and thank you, everyone. So this is ongoing work, and indeed, the slides we just made 1 minute ago. This is joint work with Betsy, who's here, and also Liz Stewart, and then Sharfstein. It's about sensitivity analysis for principal ignorability violation in estimating principal causal effects. So let me jump right in. Oh, by the way, I do not see the chat well when I'm talking. So please feel free to interrupt me and ask questions or comment along the way. So, okay, so this is the outline of this talk. I go over principal stratification a little bit, and to introduce the setting and the estimates, and then I talk about identification and particularly this assumption principal ignorability. I quickly introduce a couple of themes that organize this work. And then basically, I will go over the sensitivity analyses that we have developed, including those that fall into two approaches, a mean-based approach and a distribution-based approach. And that will be clear when we get there. And then we'll conclude the talk. So talking about principal stratification, it's a framework that defines effects in a setting where there is non-compliance or treatment to treatment or post-treatment events that are important. So these things complicate the study of treatment effects. So for example, people who are randomized to an intervention like a training some of them may not attend, or people who are in both arms of the study may decide to access the treatment or not. In the case of substance use treatment, one study finds that people in the different modalities of treatment actually have different rates of institutionalization. So it's unclear whether the apparent effect of treatment is due to the treatment itself or is due to institutionalization. And then there's also the issue that people die when what you want to study is the effect of some treatment on their quality of life. So in some of these cases, the usual average treatment effect may actually no longer be of interest. In some of the cases, they are not even defined. So researchers intuitively might be interested in the effect, for example, of receiving treatment rather than being assigned treatment, or the effect of the treatment given a post-treatment event. But looking at any of these sorts of effects in the usual way that analysis is done would break randomization, and we would be comparing apples to oranges. So then in comes principal stratification. This is a framework that defines groups that are called principal strata based on potential values of the post-treatment variable. For the rest of the talk, I refer to this variable as treatment received because it's the most common application. But generally, it can be any post-treatment variable. So the notation is this. Let Z denote treatment assigned, and we'll just consider a binary Z. Y is the outcome. Y1 and Y0 are the potential outcomes. S is the treatment received, which is not necessarily the same as Z. And that's exactly the issue. Let us have S1 and S0 denote the potential values of this variable S. So potential treatment received if assigned to treatment and if assigned to control. And X denotes baseline covariates. So in this framework, principal strata, denoted C, is defined based on the potential values of S, so based on S1 and S0. And as such, it is a pre-treatment variable. So then it makes sense to think about effects within the strata. So the principal causal effects are the effect of treatment assigned, but considered within subgroups of the population that are the same in C. So so there are many different settings depending on whether S is usually thought of as a binary variable, but it is not necessarily binary, doesn't have to be. It also depends on whether we define the principal strata based on just one potential value of S or both. And these are often called the one-sided or the two-sided non-compliance settings. So, and then it also depends on whether the outcome Y is well-defined generally or conditional on S. So in the example where the outcome is quality of life, it's not defined for people who are dead, right? In this work, we focus on a pretty simple setting where S is binary, and we're just considering one-sided non-compliance. That's the situation where the people in the control condition cannot have access to the active treatment. So that happens in cases where the treatment is designed and implemented by the study itself and is not otherwise available, or it's about a drug that is not on the market yet, for example. And we also consider the setting only when the outcome is well-defined generally. So in this simple setting, there are two principal strata: the people who would take the treatment if they are offered, who we call compliers, and the people who would not take the treatment if offered the treatment, who we call non-compliers. And we have two principal causal effects: the complier average causal effect and the non-complier average causal effects. And we think of them both as delta C, which is the effect on stratum little c, where C equals 1 means compliers and C equals 0 means non-compliers. We'll use this example of the JOBS 2 study to illustrate the methods. Here in this study, unemployed workers were randomized to either the intervention, which is receiving a 1-week training aiming to improve job searching skills and mental health, or to the control condition where they just receive a booklet. And in this study, only about half of those who assigned to the training attended the training. And we consider we looked at 3 outcomes: work earnings and depressive symptoms, for the sake of illustrating different methods. So, okay, now identification and principal ignorability. So we're talking about this delta C, right? Which is the difference now, is the difference between within the stratum specific means of Y1 and Y0. And the identification challenge is that the effect conditions on C, but C, the principal strata, are only partially observed. So in this one-sided compliance, non-compliance setting, we know who are compliers and non-compliers in the treatment arm, but in the control arm, we don't know who are compliers and non-compliers. So C is not observed. And because of that, this first, the mean of Y1 here is identified under the standard causal inference assumptions, but the mean of Y0 is not. So then identification of this effect requires somehow identifying this mean. And there are several identification strategies. Probably most well-known and it has been around for a long time is the instrumental variable strategy, which considers the assigned treatment and instrument on the treatment received. So in the current simple setting, the assumption used in the instrumental variable strategy is the exclusion restriction assumption. And in the current setting, basically it means that the NACE is 0, because this assumption says that treatment assignment only influences the outcome through the treatment received. That means for the non-compliers, because treatment received is 0, in either case, treatment assignment doesn't have an effect on the outcome. So the assumption is essentially that the NACE is 0. So why this is appropriate in some cases, it's not appropriate in the case where treatment received is not strictly binary. It is quite common actually. In a lot of situations, the intervention condition may be quite complex, but for convenience, researchers may use the one most important component of the intervention to define compliance. It's also very common for people to dichotomize a continuous participation variable to define, if you participate above a certain level, you are defined as compliers, and under you're defined as non-compliers. And it doesn't allow a bunch of other effects. Principal ignorability is another identification strategy. The assumption is basically that you have a rich enough set of covariates X, such that conditional on this X, the principal strata are independent of the potential outcome under control. Or simply that the potential outcome is mean independent of principal strata conditional on X. This assumption is appealing if we have rich covariate data. And in a lot of cases, studies have rich covariate data. It justifies what has become to be known now as the principal score weighting method. It doesn't assume that the NACE is 0, so it may be useful where the exclusion restriction assumption is not justified. And there are a couple of other strategies that are quite stringent, or like this last one is even very unrealistic. So in this landscape, we believe that principal ignorability is an important identification assumption. That's why we are focused on it. But because it's an untestable assumption, sorry, I cannot speak today, we need sensitivity analysis, and that's the topic of this work. Okay. So before we think about sensitivity analysis, I just want to zoom in to the identification problem and to see exactly what is achieved by the principal ignorability assumption. So we are contrasting two potential outcome means, Y1 and Y0. And each of them can be written this way. Don't worry too much about the details. Basically, this depends on this piece, which is usually called the principal score. And this is just a conditional mean outcome function. So the situation is that under the standard causal inference assumptions, the mean of Y1 is identified because these two pieces are identified from data, but the mean of Y0 is not identified because mu0C. So if this is 0, this is mu0C, this piece is not identified. And that is why this potential outcome mean is not identified. So that's the problem. So more precisely, we have the problem of one equation with two unknown. So this is both of these pieces here are the mean of Y0 among compliers and among non-compliers. And they're now mixed up in a mixture of the Y0 for control people. And so this one here is the mean that doesn't condition on C, and that is identified. But these two pieces which we need are not identified. So we have one equation with two unknowns. And the PI assumption does something very simple. It essentially assumes that your two unknowns are equal to each other. And because of that, they are both equal to mu0x. So any sensitivity analysis will need to replace this assumption with something else, right? In order to, so that you can combine with this equation with two unknowns, if you just combine another piece and then you have two equations with two unknowns, and you can identify mu0C, and thus identify the mean of Y0 for the stratum. So let's look quickly at the existing sensitivity analysis. And the most important one is this one. So Ding and Liu, in a huge paper that covers a lot of content, has a little piece that uses a mean ratio sensitivity parameter. So rather than assuming that these two means are the same, they assume that this ratio is equal to something that ranges on a plausible range. So this is the sensitivity parameter. And using that, they propose an estimator that modifies a weighting estimator. So this is the first sensitivity analysis that we know of. Limitation of this sensitivity analysis is that when you use it with a binary or bounded outcome, it may predict out of range. So you need to be very careful about what range of this parameter you looked at. And this motivates us to develop methods that use a range of sensitivity parameters. And let me skip the next one. So, okay, so now the beginning of our work, just a couple of themes that organize it. Well, actually two themes. One is two approaches and two is three estimator types. So we'll use two approaches that anchor on and deviate from two versions of the PI assumption. The mean version, which just says that these two means are equal, and the distribution version, which says that principal stratum is independent of Y0 given covariates. The second theme is that we start from the assumption that, or the observation that most of the time when a sensitivity analysis is done, it follows a mean analysis, and it is sort of secondary to a mean analysis based on the assumption. So we consider sensitivity analysis as a modification of the mean analysis. And we consider different types of estimators that are used for the mean analysis. so that we can tailor the sensitivity analysis for each type. Or at least that's the hope. And we managed to do that to some degree. Okay, so the first type of estimators we think of as roughly outcome regression estimators. These are estimators that estimate mu0x. And why do we have mu0x here? It's because principal ignorability tells us that mu0cx is equal to mu0x, right? So the first type estimates mu0x in order to first estimate the stratum-specific effects conditional on covariates, and then aggregate them to estimate the marginal effects. So examples here, you know, this is the principal score weighting estimator, where basically mu1c hat minus mu0 hat as functions of x is the effect for the principal stratum, but conditional on x. And then you do this weighted average here to aggregate to estimate the delta C. So for this type of estimators, the sensitivity analysis technique that we hope to use is simply to replace this bit by whatever is the identification result of mu0c under the sensitivity assumption. So that's type A. The second type includes a specific type of influence function-based estimators. Although not all influence function-based estimators belongs in this type. So here, now I need a little more explanation here. So recall that for delta C, we're contrasting these two potential outcome means, right? And we can write these out, you know, with each one with a numerator and a denominator. And again, don't worry about the details, just notice that there are two numerators here, nu1c and nu0c, and then there's a denominator here, delta C. So this type, an estimator, this type is basically something that can be expressed as a combination of IF-based estimators of these three pieces, specifically in this form. And for these estimators, the sensitivity analysis technique is simply to replace this piece, which is about this here, which has PI on it because it's based on PI, with an IF-based estimator of mu0c under the sensitivity assumption. That's it. So at least we have ideas for type A and type B. And then type C is kind of the catch-all, the remaining that do not estimate mu0x, you know, and that includes some pretty nice estimators like the pure weighting estimators, among others. Here for this type, we do not have a specific sensitivity analysis technique, and we'll just have to consider case by case. So that's it. That's the second theme, 3 estimator types. Okay, now we are ready to talk about the sensitivity analysis that we have developed. So let's start first with the mean-based approach. So in one moment. So in this mean-based sensitivity analysis approach, we are going to use 3 ratio type and 1 difference type sensitivity parameters, just to expand the options that users can choose from. So let's start with the ratio type sensitivity parameters. So recall that the PI assumption, the mean version of it, just says that these two mean are equal to each other. Now, for a binary variable, we would like to propose using an odds ratio sensitivity parameter, which is just this. Basically, this is the odds of the odds of y0 equals 1, comparing, so conditional on being a complier, that's the top, and then that's the bottom is the odds of y0 equals 1 for non-compliers. That odds ratio is equal to rho for some range of rho. The next assumption uses a generalized version of the odds ratio, which we call the generalized odds ratio. And the motivation for this is that it can be used with outcomes that are bounded on both ends. So here L and H are the lower and the upper bounds of y0. And this form is basically just this. Let's just think about L being 0 and H being 1, and you get the odds ratio back. The third one is the mean ratio sensitivity parameter. We have already seen this in Ding and Lu's sensitivity analysis. So the idea here is that these different parameters can be used with different types of outcome. So this plot just gives a sense of what different GOR values, generalized odds ratio values, imply about the connection between mu00 and mu01. So on the left-hand side here, you have generalized odds ratios that are smaller than 1. On the right-hand side here, they are greater than 1. Just different values. And so the dot here, sorry, let me not talk about the dot first. So all of the hollow points here are mu00, and all of the solid points here are mu01. And these lines just show you the connection. So if we assume that the GOR is 1.5, these are the connections. The other thing is we give an example here of a point, the blue point here, that has a mu0, actually the mean of y0 given x not conditional on C is, halfway between L and H, or you can think about it as 0.5 if we're thinking about a binary variable. And a principal score here of 0.25. And this point, with this point, the GOR implies different values of mu00 and mu01 depicted in pink. Right. So, okay. So with these three, any of these three assumptions combined with that one equation with two unknowns gives you two equations, and you can solve them and you can have identification results. No point in looking at these in detail. So these are just results for the different assumptions. So basically, well, considering the three estimator types, all of the three assumptions allow using the two techniques of replacing mu0x and replacing the IFB estimator of mu0c for type A and type B estimators. The OR and GOR assumptions unfortunately don't provide a simple modification for type C estimators, but the MR one with a simpler result gives a simple modification, which is just to scale the outcome in control units by a factor of this before implementing whatever estimator you want to implement for the mean analysis. So that's simple. So, okay, so a little bit of data illustration. In jobs 2, so we're considering three outcomes. One is work for pay is a binary outcome. earnings is a positive outcome with this actual range. And then depressive symptom is on a scale from 1 to 5, so bounded on both ends. The PI-based analysis, so this is the main analysis, shows that for compliers, the intervention, it looks like the intervention increased work and earning and reduce depressive symptoms. For non-compliers, the effects are close to null and not statistically significant. So this may be a case where the ER assumption, exclusion restriction assumption may hold, but the nice thing about this other approach is that you don't have to assume that NACE is exactly 0 and shift all of the difference to the CICE, right? Anyway, so for the sensitivity analysis, the paper goes into a lot more details about the parameter range and all that. Let me just quickly show the structure of this plot. So let's just look at the first plot here. Basically, the upper panel is the effect, shows the effect, and the lower panel shows the potential outcome means, where the red is the mean of Y1, so that's just constant. The blue shows the mean of Y0, which varies with the sensitivity parameter. On the left-hand side, you have non-compliers. On the right-hand side, you have compliers. The vertical line at 1 shows you the mean analysis. So this is the PI-based estimates, right? The PI-based estimate of the mean Y1 and Y0, and the PI-based estimate of the effect. And as the sensitivity parameter is on the right side of 1, that means that the mean Y0 is greater than the point here, and the causal effect is lower than what the PI-based analysis suggests. So there's actually a lot to talk about here, but for the sake of time, I'm going to skip. We did this for work for pay, we use an OR. For depressive symptom, we use the GOR. And for earnings, I mean, we could also use a GOR, but because we often think about, positive outcomes as we often think about kind of ratio sort of effects with positive outcomes. So we use an MR based sensitivity analysis here, and talk at length in the paper about the struggle with considering what range to consider for the sensitivity parameter. But we may come back to that a bit later. Okay. So in addition to those ratio type sensitivity parameters, there may be situations where you say, I'm not sure if the difference is on sort of a ratio scale like that. Maybe I'm more comfortable thinking about it on a difference scale. And so here we use a difference type sensitivity parameter. And so just a little bit of additional notation, let sigma squared 0c be the variance of Y0 given X within principal stratum, and sigma 0 squared X without C here denote the variance of Y0 given X ignoring stratum. Okay, so here we propose using a standardized mean difference, where the numerator is just the difference, and the denominator is sort of a combined, like an average standard deviation, a quadratic mean of two standard deviations, two within stratum standard deviations here. And so if we take this as the sensitivity parameter, we say it equals to eta for some range of eta, you know, say from negative 0.5 to 0.5 or something like that. The standardization gives you a sense of scale. So it's unlikely that you choose something too large. For example, eta of 3 would be really extreme. Anyway, this assumption only partially identifies mu0 Cx, however. So we also consider supplementing it with an equal variance assumption, which is the assumption that the two within stratum variances of y0 given x are equal, just for convenience. So under that assumption, then we have point identification. And actually this results implies that the true delta C, if the sensitivity assumption holds, is shifted away from what we have under PI by this amount. And by the way, if we don't assume equal variance, we don't get this point estimation, but we get bounds. So in this case, instead of focusing on the types A, B, C estimators, for estimation, we actually just focus on this difference here. And for that, you can use either plug-in estimation or influence function-based estimation. So, and that is that. So that's what we have for the mean-based sensitivity analysis. Now, the last bit of the talk. So all of those sensitivity assumptions using the mean ratio, odds ratio, and generalized odds ratio, and mean difference sensitivity parameters, they're all about the conditional means. And for continuous outcomes, like one limitation is that there may be values of the sensitivity parameter that conflict with the distribution of y0 given x. So now we would like to take an approach that is fully informed by this distribution of y0 given x so that it doesn't conflict with it. So this approach starts from the distribution version of PI, which says that principal strata are independent of y0 given x. And that means we want a sensitivity assumption that allows y0 and c to be dependent given x. That helps identify mu0 Cx. And here I just want to note that in the unobserved confounding sensitivity analysis for unobserved confounding or non-ignorable missingness, an assumption that is used quite a lot is the exponential tilting assumption. And this technique, if we apply it here, it would relate the probability of C given x and y0 to a simple function of y0 and the sensitivity parameter. But in this setting where we have a mixture that is observed and we want to identify the components of mixture, unfortunately, that assumption is not enough to identify the components. So we need to do something else. So what we do is a two-step construction. First, some additional notation. So let pi tilde 1, a function of x and y0, denote the probability of being a complier given both x and y0. And we're going to use shorthand just pi tilde 1. And so we can think about this as a, earlier we said that probability of C equals 1 given x is the principal score. We can think about this as an outcome-specific principal score. And then the pi 1 given x is like an outcome agnostic principal score. So our construction involves two steps. The step one is to assume a distribution for pi tilde 1 given x that has mean pi 1 given x. So it needs to be anchored on this because this is observed, right? This is identified from data. So we want this distribution that has this mean. It allows pi tilde 1 to vary around this mean. And this distribution is indexed by a dispersion parameter that we can use as a sensitivity parameter. And then step 2 is, given this distribution that we have assumed, we want to connect y0 to pi tilde 1 in some way that induces an association between y0 and c. So, okay, so for step 1, we borrow Victor Weitz. I hope I say his name wrong. I hope I say his name right. We borrow his idea of using the beta distribution. So we're going to assume that pi tilde 1 is distributed beta with these shape parameters. So it has mean pi 1x. And kappa can be thought of as a dispersion parameter, and its range is from 0 to 1. So in this picture here, we are showing for different kappa values how spread these distributions are for several of the pi 1x values. So here, so the mass here is, you know, if kappa is 0, you get this mass at pi 1x, right? And you notice here that even with what looks like small kappa, you already have quite a bit of spread. So you don't want kappa to be very large. So in our application, we pick the max kappa to be 0.05, which I believe is this curve here. Anyway, so that's step 1. We assume this distribution, this beta distribution. And then with step 2, what we do is to use quantile to quantile mapping. So connect y0, the quantiles of y0 to the quantile of pi tilde 1. And if we assume that the y0c association is positive, the mapping would be same quantiles, right? So 90% on the y0 distribution connected with 90% percentile on the pi tilde distribution. If we assume the distribution is negative, then we use opposite quantiles mapping. So basically, then we replace the PI assumption with this sensitivity assumption, where it's just, you know, so beta here is the quantile function for this beta. And F here is the CDF for y0 given x, right? So it's just quantile to quantile or quantile to opposite quantile, depending on the assumed sign of the association. So there we have identification, and so this method requires estimating the distribution of the outcome given x in the control condition. That's the additional bit that needs to be estimated. And then based on that, we can estimate mu0 cx using a pretty simple numerical integration procedure. So I just want to show the result. So this is the result for the earnings outcome and the depressive symptom outcomes if we use this method. Note that so just to compare, I'm going to flip to the previous results using the mean-based method. And sorry, just ignore the first panel here and look at these two. Okay, now I'm going to flip back. There's much less variation here when using this method, because how much the effect can change is read in by, you know, the information about the distribution of y0 given x. So yeah, see the difference. So that's it. So those are the methods that we have developed for sensitivity analysis for principal ignorability violation. And our simplest conclusion is that with this work, we have expanded solutions for this sort of sensitivity analysis, which we highly recommend should be done whenever doing an analysis using the PI assumption. And of course, there are, you know, there's room to expand to two-sided noncompliance. In the paper, we also talk about some interesting things that we notice about finite sample bias that we wonder whether is generally applicable to other sensitivity analyses as well, and things like that. But this is basically the main story. So thank you for hanging with me, and I take questions now. And we also appreciate it if you have any comments or thoughts, you know, now or later, that could be very helpful to us. And before I stop, I apologize for my not being able to speak today. That's it.
Thanks, Trang.
Thank you.
Any questions, everyone?
I guess not.
Thanks again, Trang. It was very thorough and a lot of details, which maybe explains why there are no questions.
Well, actually, this so maybe I was trying to go too fast because I was afraid that I would run out of time. So if anybody has any, you know, comment about which part you know, I lost you on or something like that, that may help with like make this a little more useful or interesting. And I don't want to put you on the spot, Brian, but because you mentioned that you might have some use for this, I would like to hear your reaction.
So I think what you're talking about is beyond what I'm looking at, but I'm working on a randomized trial where there's poor compliance. So it's a real issue. So we'll be looking at some of the general methods that you talk about here. So I may become talking to you about that in a little bit. I guess I'm also curious about if I could just ask about the non-complier average causal effect, and what does that represent really? If you can describe that a little bit more for me.
Oh, great question. So I think the labels complier and non-complier kind of just in some way convenient labels. Like in specific applications, like other labels may be more useful. So for example, I know of a study where people are involved in this activity for the whole year. However, they're counted on the hours that they are involved, and then the investigators decide to put a cutoff at some point. Like the median is usual, but it can be something else. And then if we use the two groups, if we call the two groups compliers and non-compliers, it's kind of misleading, right? Like the real labels should be, you know, high participation and low participation or something like that. And if we believe that, you know, I mean, if the theory is that participation in this sort of activity has some effect on the intended outcome, then it's plausible that the low participation group may have some non-zero effect, right? And so even though here we call it we call them non-compliers and we call the effect NACE, is really the effect on that group that would participate at that level. Oh, hi. Yeah, so that's why I'm saying that it's very common to see in the literature that, like in the applied literature, that people dichotomize a, you know, participation variable, but then assume exclusion restriction and say basically we think that the effect for that group is 0, which may be benign if you don't care about the effect at that level of participation. But the thing that is not benign about it is that the analysis then shifts all of the differences in outcome to the higher group, right? So it happens that the NACE is actually not 0, but small, and even non-significant, but not 0. That difference will be shifted over to the CICE, and it overestimates the CICE. I have even seen a data set where, like, I couldn't figure it out, but when you do the analysis using principal, like when you don't assume that the NACE is 0, it looks like the NACE is larger than the CICE. But if you don't think about it, you assume that the NACE is 0, suddenly the CICE seems very big. You know, so yeah, I think exclusion restriction is great when it makes sense that it holds. Yeah,
that makes sense. Thank you.
Yeah,
that's great. Thank you.
So principal ignorability came out later, so it hasn't caught up very, you know, much compared to the instrumental variable strategy. So it's kind of weird that I sort of have to sell it before selling sensitivity analysis. But I think it's kind of, you know, the one reasonable thing, just by common sense, that you can do. Oh, there is something in the chat. Oh, Brian. Thank you, Brian. Other Brian. Yep, that's all I have, and we hope to, I know it's a very specific case, and sensitivity analysis is even makes it more specific. But we hope to post this paper soon and publish it. Sorry, not publish it, submit it soon. Yeah. Thank you, everyone.
Great, let's thank Trang again.
Thank you.
Thank you so much.
Mostly, thank you.
Thank you, everyone.
Thank you.